When we talk about coordination compound, the name is coordination because there are coordinate bonds. Simple. So there is one central metal atom. So you have metal atom in the middle. And then you have ligands connected to it. Whatever is connected to it, that is known as ligand. So when we talk about coordination compounds, earlier they were known as complex compounds. Due to just their complexity, they look like complex. So that's why complex compounds, but now the name is coordination compound. Still in the books you will get complex and coordinate both written here. Okay? So in this you have one metal atom, and this metal atom can be surrounded by some other neutral molecules or ions. So this is neutral molecule, this is neutral molecule, but if it is attached with chlorine, this will be ion. Okay? So it will be like that. And you see, I am just drawing the arrows. Arrows means these are coordinate bonds. In these coordinate bonds, what is coordinate bond? Coordinate bond is that bond when both the electrons are provided by one species. It is exactly same as covalent bond. The properties are not different. Properties are exactly same as covalent bond. The only means both the electrons are shared by both. But the difference is that both the electrons are provided by one. So here, these electrons, these two electrons are being provided by A only. So that's why the arrow. A provides both of these electrons being shared by both. So here, similarly, those particular neutral molecules or ions will provide the electrons which can have either the lone pair or extra electrons. So here in ammonia, you can see NH3. Nitrogen has two excess electrons. In H2O, you have two lone pairs on oxygen. Okay. So those molecules or ions which have a lone pair, they provide electrons to central metal atom, and that's how these coordination compounds are formed. Then there is Werners theory of coordination compounds. Means how you can explain why do we call it these are coordinate compounds? What is difference from ordinary compounds? The difference from ordinary compounds in terms of that they look like that they are double salt. Double salt means you have one salt, say NaCl, another salt MgCl2, a combination of that. So it looks like these are combination of two salts, but they are not actually double salts. Okay, they are not actually double salts. So what is the difference? The difference was explained by Werner, and this is Werner's theory of coordination compounds. This theory says that there are two valencies. Till now we are talking about only one valency, but Werner said based on experiments that there are actually primary and secondary valence, not just one. So what is primary valence? That is something we have been doing. So for example, if I say I have NaCl, so the valency of chlorine will be how much? 1. 1 because it will gain 1 electron, right? So what is the secondary valence? The secondary valence was explained on the basis of that this is normal case, CrCl3, CoCl2, PdCl2. In all cases, the primary valence will be here 3, here 2, here 2, like this. Then the concept of secondary valence. What happened? In a series of compounds of cobalt chloride with ammonia, it was found that some of the chloride ions could be precipitated as AgCl on adding excess silver nitrate, but some remained in the solution, dissolved in the solution. They did not ionize. What I am saying, understand what I am saying. If I have cobalt chloride, so normally cobalt chloride, you will say what it will be. It will be CoCl2, depending on its valence. Okay. But what happened that in that case, in the experiment, few Cl2 a few chlorides got out of this compound, got ionized and reacted with Ag silver to give you AgCl, but others did not. So this gave him a hint of that. So what actually happened? 1 mole of CuCl3 dot 6 NH3 yellow gave 3 moles of AgCl. And how many chlorines are there? 3. And you got 3. Absolutely fine. There is no problem. But when CuCl3 5NH2 got reacted with AgCl, only 2 moles of AgCl were found. So if I have 3 chlorides here, I should have got 3 AgCl. Okay. Similarly here, I have 3 chlorides. I should have got 3 moles of AgCl, but I am getting only 1. These two are actually same, but the difference is in their geometry. So due to their geometry, the formula is exactly same. One is green, the other one is violet. Okay. So difference in their structure only. Both gave only 1 mole, and it was explained by Werner. How he explained it? He said, actually, in case of this one, in this case, it is actually CO, then Cl, and then all NH3 5 attached to cobalt, and only 2 chlorines are outside. So it is ionic compound. So he said that actually this is the whole cation and this Cl2 is anion. Instead of a structure like this, he said this is the structure. So those ions or neutral molecules which are attached to central metal atom, cobalt is central metal atom here. These are non-ionizable. This is non-ionizable, means this is not ionic part. This is ionic part. Only these two will get ionized, will be available as ions. That's why you are getting only 2 moles of AgCl. Means 1 chlorine is inside the square brackets. Anything in the square bracket here is known as coordination entity or coordination polyhedra also. Okay. So this is the coordination part. The other is ionizable part. So what he said, Werner said this is the primary valence which can get ionized, and the one which cannot get ionized is a secondary valence. So what will be the secondary valence? Can you guess what will be the secondary valence here in this case? Huh? No, how many? Okay. Secondary valence. Okay, I will explain. Okay, so that's why I asked. Okay. 6 groups. So these observations can be explained. So whatever I showed you here, I am now explaining it. Okay. 6 groups in all, either chloride ions or ammonia molecule, both remained bonded to the cobalt during the reaction. So there were 5 ammonia molecules as well. It was not only 1 chlorine. I am going back. Is this only chlorine attached to this cobalt? These 5 ammonia are also attached to cobalt within the coordination sphere. Okay. So the compounds are formulated in such a way that some atoms in combined form within the square brackets form a single entity which does not dissociate under the reaction conditions, means they are non-ionizable. Werner proposed the term secondary valence for the number of groups bound directly to the metal ion. Now I am asking the same question. What is the secondary valence in that case? Do you still say 1? There are 6 ligands attached to central metal atom. Yes, Tanishi, good. So in each of these examples, the secondary valence are 6. Secondary valence is not changing. If chlorine is not there in the coordination polyhedra, then you have 6 ammonia. Now I'm telling you another important point from where questions are asked. Here also, you have out of these 3, you have 2 ionizable. It means 1 is non-ionizable plus 5, total 6 is still. Out of these 3, 1 is ionizable. It means 2 non-ionizable plus these 4 is still 6. Similarly, here also 2 non-ionizable and 4 NH3 attached to metal, central metal, total 6. So this gives you another point, important point, that the secondary valence of any metal is constant. It will not change. The compound can change. Compound can be different. It may not be chlorine and ammonia. It can be anything else, something else also. Even then, the secondary valence of any metal will never change. It will be constant. It will be 6. Simple. Okay. So irrespective of the compound, if you are asked what is the secondary valence of cobalt, and if any one compound is given, on that basis you can say it will always be 6. Only whatever is inside the square bracket, that will decide the secondary valence. Outside square bracket, primary valence. Okay. So this is another point, and how it is asked. Sometimes it is asked which type of electrolyte it is. So they are specifically, and in MCQ type question, it will be 1:3 electrolyte, or 1:2, 1:1, or 1:1. वही बता रहा हूँ. I'm coming to that. It is simply saying that if you take 1 mole of this one, 1 mole of this one, how many, just a second. Right. How many primary valence will be obtained? How many will actually get ionized? Remember, this is not telling you total number of ions, because if you consider total number of ions in this case, and that is also separate question which is asked. On ionization, I am considering this part. Okay. On ionization, you will get CO NH3 whole 6 as cation, and you will get 3Cl minus as anions, because in this case the primary valence is 3. So total number of ions will be 4. This cation and these 3 anions. But the ratio is not about it. Ratio is 1 mole of coordination compound gives you how many primary valence. Are you getting it? How many primary valence? So this is 1:3 electrolyte, because 1 mole of it will give you 3 primary ions. 1 mole of this will give you 2 primary ions. 1 mole of this will give you 1 mole of primary ion. Can you remember that simple thing? Okay. And 1 MCQ type question done with. Simple. So I'm basically, this is repetition of what I have said, but I will anyway repeat it. In coordination compounds, metals show 2 types of linkages, valencies, primary and secondary. The primary valencies are normally ionizable and satisfied by negative ions. The secondary valence are non-ionizable. So these are satisfied by neutral molecules or negative ions inside the square brackets. And remember, these are known as ligands. The term is used as ligands. So you have central metal, and this chapter is very, very easy if you just listen to me during the class only. You just can start solving the questions after the class. Okay. So central metal, and then you have ligands. These ligands can be negative anions or neutral. Both are possibilities. I told you why. Because even if it is neutral, it has the lone pair, it can donate lone pair. So that's why coordinate bond is possible. Then the next one. The secondary valence is equal to the coordination number and is fixed for a metal. It is always fixed. And important point here is equal to the coordination number, means same is coordination number also. Whatever is secondary valence, that can be asked as what is the coordination number of this compound. So what you will write, if you are asked about what is the coordination number of this compound, you will write what is the secondary valence of this compound. Clear? So coordination number is simply the number of ligands which will be attached. No, Kasak, you don't need to learn their name according to their color. No. Okay. We will be talking about how to write the IUPAC names of these ones, how to write the formula if IUPAC name is given. That is something important, but not on the basis of previous slide. Why? Second point is just coordination number is actually secondary valence. Simple. Okay. The ions groups bound by the secondary linkages to the metal have characteristic spatial arrangement. This is almost same thing what you have done in 11th grade in chemical bonding. In chemical bonding, we talked about tetrahedral structure, trigonal pyramidal structure, okay, trigonal bipyramidal structure, exactly same thing. Because if 6 are connected, 6 ligands are connected, what structure should they follow? Apply the same logic, BSEPR theory. Do you remember that? If we have 6, then 6. 6 square bipyramidal, right? Okay, so if it is 6, it will be octahedral or square bipyramidal. Same thing we will apply here also. Octahedral, kasa good. So whether you say square bipyramidal or you say octahedral, it is same thing, and same logic will be applied here as well. Whatever is inside the square bracket, it is known as polyhedron. We call it polyhedron when polyhedra is plural. Okay, polyhedron when we are talking about specifically their spatial arrangement, means 3D structure. So if we are talking about 3D structure, we call it polyhedron. Otherwise, we normally call it coordination entity, nothing else. Okay? Coordination entity inside the square brackets. But if we are showing the 3D structure inside it, then we will call it polyhedron, coordination polyhedron. The species within the square brackets are coordination entity. This is something I have already told you, coordination entity, or if the spatial arrangement, coordination polyhedron, or complex, and the ions outside the square bracket are counter ions. So primary valence is related to what? Counter ions. You need to remember this term. Counter ions. Counter ions are those ones which are primary valence. Nahi, bahar wale. The ions outside the square brackets. So you have square brackets outside. This is counter ion. Inside coordination entities. But if I am saying just coordination entity, it means I am talking about whole coordination sphere. So there are different terms I will be using. I will be using coordination sphere, I will be using coordination polyhedron, and I will be using coordination entity. Then it is same thing. But if I am saying coordination entities, then it means I am talking about central metal atom as well. I am talking about all the ligands, whether those are ions or neutral atom. Entities means all the parts of the coordination sphere. So different terms I will be using there. Now the question, okay, and I need answer from you. Okay? Here what is given, you have compound, and with this compound moles of AgCl precipitated per mole of the compound with excess of AgNO3 means you don't have insufficient AgNO3. AgNO3 is sufficient. Okay, whatever amount you need, you need to tell the secondary valence. So tell me secondary valence. What should be secondary valence in first case if 2 moles of AgCl precipitated? Write your answer. Right. Don't tell me, because if you say, others will listen to you. Write in the chat box, everyone. What should be the secondary valence if 2 moles are precipitated? No. Yes, your answer is correct. Kavish, correct. Here. Nine. But it's so easy. So very easy. Okay. Okay. Tanishi, Savya, Kartike, Devyansh, correct. And I hope you are not. Why you people give me correct answers when you join online, and when you are offline, you are not able to? I hope you are not looking onto the internet or anywhere else. Okay. So try to understand. 2 moles of AgCl precipitated. It means all these got ionized. Only then 2 moles. You got 2 moles of AgCl. It means it was something like this. Pd, whatever is there. And here you have 2Cl minus, or you can say Cl2. 2Cl minus. It means only then you will get 2 moles of AgCl if you have 2 chlorides outside. It means you don't have any chlorine inside. You have just NH3O4 inside. Did you get that or not? Only NH3O4 is inside. It means what is the coordination number? Secondary valence 4. Only 4 ligands are there. Secondary valence is coordination number. So it means 4 is the correct answer. Any confusion here? Ananya, is that clear or not? Ananya, I am asking you, is that clear or not?
Sir. Yes, sir.
Okay, if it is clear, then tell me for the second one and write it. Don't tell me. For second one, what is the secondary valence? Apply the same approach. Second one, correct. समझ अच्छा तुमने सारे लिख दिए, तुम एकदम से स्मार्ट हो गए वेदांत हैं, अभी समझ गए अभी। अच्छा हाँ, एकदम से स्मार्ट हो गए तुम। नहीं, तुम्हारे सारे सही नहीं है, इसलिए तो मैंने बोला नहीं। यस करेक्ट, काविश ऑल्सो ऑल करेक्ट। गुड। Okay, now let me see. Okay. Kasak, I will explain the second one. It will be clear. Okay. Kartike, Tanishi, Prakriti, Arna. Correct answers. Okay. For the second one. Now here again 2 moles of AgCl got precipitated. So 2 moles of AgCl means you should get 2Cl minus ionized, so that 2Ag plus will get reacted. So it means here all these Cl2 are ionized. These cannot be inside, the brackets, coordination sphere. They will get ionized. So it means how many H2O are attached to nickel? It means the formula is this is the formula. Chlorines are outside, 6 H2O inside. So it means 6 ligands. 6 is the answer there then. Similarly, the next one, 0, no AgCl. It means it does not have any chlorines outside. So all these 4 chlorines are inside, all these 2 HCl inside. So all 6 inside, it means it will be 6. Similarly, next one chlorine is outside, it means 2 chlorines inside, 4 NH3, 2 plus 4, again 6. Then PtCl2, no chlorine ionized, it means these 2 inside, this 2 inside, 4. Kasak, is that clear? Now, what I am saying on the basis of ionization, okay. So this simple question, when it appears, normally it appears with 2 parts. Okay, any 2 will be asked. Okay, not these what given, any 2 parts, and it will appear in 1 or 2 marks both. So it is possible that both have 0.5 marks or both have 1. So there is no hard and fast rule. Now, difference between double salt and a complex. Complex means coordination compound. What is the difference? And by now you should have understood the difference, at least what is that peculiar part which makes the coordination compounds different from salts. The difference is that there are non-ionizable ions. And that's what I am explaining now. That's what the topic is. So the difference which makes the coordination compounds different from salts is they have non-ionizable compounds, non-ionizable parts. But in salts, everything will be ionizable. If I am saying it's salt, it means it is not complex compound. So all species will get ionized in double salt. So double salt means it is formation of 2 salts. It is a combination of 2 salts. So if I am talking about, say, these compounds, okay, double salts such as KCl, MgCl2, and in hydrated form, normally it remains like this, okay. So there you have 6H2. In case of coordination compounds, also you have H2O, 6H2O, 5H2O, like that. Then more salt, FeSO4, NH4 whole twice SO4, and 6H2. Then potash alum, KAlSO4 whole twice, 12H2. Then remember, KAlSO4 whole twice means we are talking about that it has both sulfates of potassium and aluminum it can have. But the point here is that they will dissociate into simple ions, means everything will get dissociated. So if I consider this part, it will be Fe2 plus, SO4 2 minus, NH4 plus, then again SO4 anyway I have considered. So it will get dissociated in all the parts. So there will not be any non-ionizable part. Everything will get ionized. Okay. So every part will get ionized in case of double salts, even though they look like coordination compounds. They look like coordination compounds, but there is huge difference. The first difference, which is most evident and not always true, but sometimes it might be different also. The most evident is that instead of 1, you have 2 metal atoms here. In double salts, you have 2 metal atoms. So similarly here, or you can say in, that's why I said almost. Here it is just 1, but the other one is anyway cationic part, even if it is not metal. Here you have 2 metal atoms. So this is most evident part.
So there are 2 cationic parts for sure.
2 cationic parts will be there. Okay. In few cases, the reason I said that in most of the cases this is true, because in few cases you can have 2 different salts of same metal also. In that case, it can be single metal, but that is actually 2 compounds. Okay? 2 compounds will be there. So if you are asked what is the difference is very simple, but you need to remember these examples. So write these examples. This is asked, this question is asked, that which out of the following are coordination compounds and which are double salts. So just memorize these 3. carnellite, Morse salt, potash alum. Complex ions such as FeCN6, 4 minus, or K4FeCN6 do not dissociate into Fe2 plus and Cn minus. They will not get dissociated. Then definitions of some important terms which I have been using. Basically, I have already used these terms, so I'm just going through them very quickly. A coordination entity means whatever is inside the square brackets. That is also said as coordination sphere or coordination polyhedron, depending on what I am talking about. Coordination polyhedron only if I am talking about the structure. Okay, so I will tell you when we call it coordination polyhedron. Okay. Central atom or ion inside the polyhedron, that is one of the coordination entities, central metal atom. Then ligands which are attached to central metal atom. These can be ions, these can be neutral atoms. So whether neutral or whether simple molecules, neutral or ions, these are called ligands connected to central metal atoms. So these are neutral. For example, this is ionic, anionic only. Now this is important. Unidentate. Unidentate ligand means which will connect only from one atom. So when I say uni means one. It means only one site from where the ligand can connect to central metal atom. For example, chlorine, H2O, NH3. H2O has lone pair on oxygen, so it can connect through oxygen only. NH3 has lone pair on nitrogen, so only nitrogen can donate lone pair. So only one site is there from where it can connect to the central metal atom. Didentate means there are two such sites. So same molecule or ion has two different sites from where it can connect to the central metal atom. So for example,
Is it different from ambidentate?
yes, it is different from ambidentate. Okay. I will be coming to ambidentate. So for example, here you have nitrogen lone pair and you have nitrogen lone pair. This is ethane 1,2-diamine. Ethane 1,2-diamine. It means it will get connected to central metal atom from these two sides. And both will be connected. It's not that one at a time. So remember, in didentate, this is the difference when I will be coming to ambidentate. Okay, why students remain confused between these two? Because they both say that they have two sides from where they can get connected. But in case of didentate, both will be connected to the central metal atom. Same time, both are connected. Okay, if I am saying both, it means both are connected. Similarly, oxalate ion, this one. So if it is something like COO minus, when it will get connected, this minus will disappear and both will be connected to central metal atom. Didentate. Okay. So means this is same oxalate. Okay. Oxalate has two sides, this oxygen and this oxygen. Both these oxygens will donate their electrons to central metal atom and will form coordinate bond. If you have COO, it has two, this one and this one. These two will give the electrons to the central metal atom. So there will be two ligands here in just one compound. So one ligand is there, but it will have two coordinate bonds. Simple. One ligand, two coordinate bonds. Polydentate means there are multiple 3, 4, 5. Okay. So polydentate, more than. So suppose I talk about this one. Okay. And CH2, CH2, NH3 whole thrice. So it is something like this. There are three CH2, CH2, NH2. Then here again CH2, CH2, NH2. Then here again CH2, CH2, NH2. Now if you see nitrogen, nitrogen will have lone pair. So here it will have lone pair. Here it will have lone pair. Here it will have lone pair. And here also it will have lone pair. Nitrogen has total 5 electrons in valence shell, 3 are occupied, and 2 will form in lone pair. However, all 4 can get attached. Okay, so if you are asked how many ligands will be there, so but polydentate means whether it will be tridentate or tetradentate, means 3 or 4. You will say 4, but the possibility of this one is less because this is surrounded by 3 CH2, CH2, NH2. So there is hindrance. But those questions will appear in only IIT or NEET, not in CBSE. Comparatively, which one will be more forming the coordinate bond? But it will be 4. Similarly, this one is very, very important. Ethylene diamine tetraacetate ion. Question has appeared quite a few times, okay, related to this one. Ethylene diamine tetraacetate ion is an important hexadentate ligand, hexa. Now you might be surprised why it is hexadentate. For that, there is a structure. So this is the structure of ethylene diamine tetraacetate. Here you can see this nitrogen, this nitrogen. So you have 1, 2 lone pairs, and then you have excess electrons here. All these 6 sites will form the bond, coordinate bond. All these 6 sites. So remember, even if there is some atom which has less possibility, but remember, in whenever I am talking about di, poly, all bonds will be formed. So in previous case, remember, in this case, when I said here will be less possibility, it does not mean that it will not form. I said still it will be tetradentate. Okay, so if you are asked, you will say tetradentate. The comparative study will be only for IIT and somewhat for NEET. Any confusion till here? Polydentate clear. Okay. Now chelate. Chelate is actually for polydentate. Whenever all these type of di, tri, tetra are actually known as chelate ligands. So in polydentate, if you say you have, and one more thing, when I said this one, this one. Ethane 1,2-diamine, the short form is written as EN. Ethane 1,2-diamine, normally you will get written it as in brackets EN. So it is written as short form, very short form. Okay. So if I am using ethane 1,2-diamine as one of the ligands, okay, then it will have 2 coordinate bonds connected to central metal atom, right? Because you will have 2 nitrogens here, 1 nitrogen here, another nitrogen here. Both will donate the electrons, lone pairs. Okay. This mechanism, this is known as chelate. This structure is known as chelate structure. So whenever you have more than 1 coordinate bonds attached to same central metal atom, we say this is chelate structure. These can be 2, these can be 3, 4, whatever. And this mechanism, process is known as chelation. So if you are asked what is chelation or what is chelate bond, answer is same. Polydentate ligands structure is known as chelate structure, chelate ligand. So when a di or polydentate ligand uses its 2 or more donor atoms to bind a single metal ion, it is said to be chelate ligand. So all these ethane 1,2-diamine, oxalate, EDTA, whatever we have talked about, all these are chelate ligands. Simple. So polydentate ligands are chelate ligands. Simple thing. Okay. So few points I am repeating. I am saying that these are same terms. Okay. So for example, I said secondary valence and coordination number is same thing. Coordination number, secondary valence, same thing. Coordination sphere, coordination polyhedron, same thing. Coordination entity, same thing. But coordination entities means I am talking about specific metal or ligands. Similarly here, didentate, polydentate, chelate ligands. Okay. So polydentate ligands are chelate ligands. There, how many bonds they have coordinate bond, that is called denticity. So it means didentate, denticity will be 2. Tetradentate, denticity will be 4. Hexadentate, denticity is 6. So if you are asked what is denticity, this is how many coordinate bonds are there. Now ambidentate ligand, ambidentate and didentate, these are two different things, and the only difference is that ambidentate will have 2 sites, but one at a time will be connected to the central metal atom. That's the difference. Ambidentate can have 2 or can have even more than 2. Okay. Normally we will be talking about 2. So that's why we say 2. But one at a time will be attached to the central metal atom. These are the examples. NO2 minus and SCN minus. So in case of NO2, both nitrogen and oxygen have excess electrons.
For ionic one, oxygen plus and for covalent one.
So if you say NO2, it is O like this. Do you remember that? It's like this, but still nitrogen can donate or oxygen can donate. Means there are 2 sites from where NO2 can get attached to the central metal atom one at a time. Right? One at a time. Similarly, SCN. So nitrogen can donate electron to metal or oxygen can donate electrons to metal. This is known as nitro N and this is known as nitro O. I will be using these terms when we do IUPAC naming of complex compounds, coordination compounds. So just remember, N and O actually they designate which particular atom of that ligand is connected to central metal atom. If you don't write this one in case of ambidentate, your answer will be wrong. Similarly, thiocyanato, sulfur is connected to central metal atom. And if I say nitrogen is connected, it is isothiocyanato. And you can remember it easily because Cn is cyanide and C is isocyanide. From there you can say it is isothiocyanato because nitrogen NCS is there. Sulfur in this naming is known as thio. Okay. So sulfur is thio. So is the difference between didentate and ambidentate very clear or not? This is the point where students normally make mistakes. Ambidentate means it has 2, but only one at a time. Coordination number I have already told you. Coordination number is secondary valence. Okay. Whatever is secondary valence, that is coordination number. We have talked about. Now, very important point related to coordination number, where students make mistakes. Okay. Suppose I have PT EN3. Suppose I am talking about PT EN3. Okay. 2 plus, or it can be 4 plus also, depending on which particular it is. Normally 2 plus. Okay. Now tell me, what is the coordination number here? It will be 6. Good, Kavish. Because En is dientate. And because En is dientate, it will be connected through 2 coordinate bonds. Another En will be connected through 2 coordinate bonds. Another En will be connected through 2 coordinate bonds. So it means coordination number here will be 6. Not 3, even if it looks like it is 3. Okay. Similarly, if oxalate is connected, there will be 2 bonds, 2 coordinate bonds. Okay. If it is EDTA connected, there will be total 6 by 1. Total 6, hexadentate. Okay, hexadentate. Coordination sphere, as I have already told you, it is a just coordination sphere, nothing else. Coordination polyhedron, same thing. But when we say coordination polyhedron, the only difference is we talk about these structures. That's why I said in 3D space, spatial arrangement, polyhedron means we are talking about the structure. So if I am saying like this, okay, this within the square I am writing like this, then it is called coordination polyhedron. You have actually drawn the shape of that molecule, okay, inside it. But it is still the same thing inside the square brackets. Oxidation number of central atom, this is same thing what you have done in redox reaction chapter in 11. You will apply the same approach. Whatever oxidation you have to find, you will say it is X, and other oxidation numbers you will add. And suppose I say that it is given like this, 2 plus. So you will add all the oxidation numbers here and you will say it is equal to 2 plus 2. Okay, that's what we used to do. Okay. Same thing we will do here. So suppose in this case, CuCN whole 4, 3 minus. Suppose you say, okay, copper's oxidation state is X, and we will be using it quite frequently. So just pay attention, everyone. It will be X, and then it will be 4 times Cn minus 1. It will be equal to how much? Minus 3. This is the charge. So X will be minus 4 on the other side. 4 minus 3, that is plus 1. So it means copper here is in plus 1 oxidation state, and we write it in stock notation, Cu and the oxidation state. This is called stock notation. You have done it in 11th. Huh? Minus 1 okay. It is treated as minus 1. Otherwise, you can get, you can memorize it. You should memorize it. Okay? And that's why I said you will use the information of redox reactions here. Then homoleptic and heteroleptic. Homoleptic means all the ligands are same. Hetero means different. The ligands are not same. So if I am saying CuNH3 whole 6, this is the only ligand NH3. There are 6 NH3. So it will be called homoleptic. But if I have different types of, for example, here I have NH3 and chlorine also, this will be heteroleptic. So just remember these terms: homoleptic, heteroleptic. Till now, any problem to understand this chapter? No? Good. Then writing formulas of mononuclear coordination entities means we have just one central metal atom, and that's what is in your syllabus. You need to remember few points, and specific points I will explain, because here I have written exactly what is written in NCERT. Okay, but some explanation is required, otherwise you will make mistake. if you follow exactly what is written here. The central atom is listed first. Remember, I am talking about formula, I am not talking about IUPAC naming. In case of naming, it will be different. The central metal will be actually named almost at the end. Okay, every time. But here, central atom in formula, and that's something you are looking at also. For example, CO comes first. Do you remember that? So first central metal atom is written. The ligands are then listed in alphabetical order, and this is huge confusion here. Huge confusion. Okay. Now, do you see these written in alphabetical order? No, right? And that's what NCERT says. The point here is, it is actually by their name. Yes, by their name. Okay. So this is ammonia, this is chloride. So A and C. That's how you will have to do. Polydentate ligands are also listed alphabetically. In case of abbreviated ligands, the first letter of the abbreviation is used to determine. So remember, if I use abbreviations of, then I will consider only the first letter of the abbreviation. Otherwise, first letter of the name, not of the formula. Not of the formula. The formula for the entire coordination entity, whether charged or not, is enclosed in square brackets. So coordination entity, you know, coordination entities, whatever is in the square brackets. Sometimes what might happen, this is something just we talked about in the very beginning. We said that there can be primary valence, there may not be primary valence. In few cases, do you remember that we did not get AgCl precipitated? It means nothing was outside the square brackets. Everything was inside the square bracket. So if that is the case, there won't be any charge on this one. Okay. But otherwise, if you have 2Cl minus here, 2 plus charge will be there. So this coordination entity can be neutral, may not have any charge, may have any charge. I am coming to that. Okay, examples I am coming to. When ligands are polyatomic, their formulas are enclosed in parentheses. So this is something you have already seen. Whenever I had written NH3, it was in bracket. But chlorine was not in brackets. It was written just Cl3 like this. But NH3 was written as NH3 whole 6 like this, or whole 4. So whenever I have polydentate ligand, polyatomic ligand, NH3 is polyatomic, it has nitrogen and 3 hydrogen, more than one types of atoms. So in that case, you will use parentheses. Moreover, whenever we use abbreviations, for example, for ethane 1,2-diamine, I use EN. Then EN will also be written in parentheses. And normally you will see that we write EN. We don't write ethane 1,2-diamine. So EN, if we have 3 ENs, then we will say EN whole thrice. These will be in parentheses. So ligand abbreviations are also enclosed in parentheses. There should be no space between the ligands. This is the same thing as I said in case of IUPAC naming, no space except few acids. Okay. So whenever you say carboxylic acid, then there is a space between carboxylic and acid. Otherwise, no. When the formulas of a charge coordination entity is to be written without that of counter ion, the charge is indicated outside the space. So for example, if it is CO, Cn whole 6, Cl3, it's like this. And I don't write chlorines. Then I will write here, or it is K3. It is not like that. It is, I have written it wrong. It is actually K3COCN whole 6. So here it will be 3 plus charge. If I don't write it, I will mention 3 minus charge here. Okay. It will actually be like K3 plus and COCN6 3 minus to balance the charge. If I am not writing this, I have to indicate that there is something extra which I have not written. This 3 minus indicates it means something extra is there which has not been written here. The charge of the cations is balanced by the charge of anion. So this is something very simple, that in this whole universe, everything is charge balanced. So if you have +3, there has to be -. Then IUPAC naming of mononuclear coordination compounds. So I think I had some questions here. But to your Tanya, to your question, is this clear what I talked about here? Okay, these are the examples here. Right, let me see the time. Otherwise, I will do questions first. Okay. Now there is some difference. When I say IUPAC naming, it is different from for writing the formula. Okay, formula, it is simple, it's not tough. You first, within the coordination entity, you first write the metal, okay, and then you write the ligands. In the ligands, you specifically enclose those ones in parentheses which are polyatomic. Okay, primary valence is written outside, secondary valence is written inside. Now this one very important. The cation is named first in both positively and negatively charged coordination entities. So as I said, I'm just going back. Two coordination entities we talked about here in this case. One coordination entity has negative charge, the other one has positive charge. Okay. In this case, it will be K3COCN6. In this case, it will be CrH2O6Cl3. Right. So in one case, coordination entity is anionic. In another case, coordination entity is cationic. But in both cases, when we name the cation is named first in both positively and negatively charged coordination entities. Okay, means whatever is cation, whether it is coordination entity, whether it is something else, cation will be named first. The ligands are named in an alphabetical order before the name of the central atom. Means central atom will be now written after ligands. In formula, what was the case? In formula, we had metal first, CO, metal first, and then the ligands. In case of IUPAC naming, you will write ligands in alphabetical order before the name. So these will come first, ligands will come first. This procedure is reversed from writing the formula, so it is not same. Names of the anionic ligands end in O. This is important thing, okay? If the ligand is anionic, for example, chloride, so we will write it chlorido. Okay? If it is nitrite, nitrito, oxalato, these are anionic ligands. So we will end these with O. Those of the neutral and cationic ligands are same except aqua for H2O and amine for NH3. Remember, double M. So it is not amine. This is ligand amine, A-M-M-I-N-E. Amine is A-M-I-N-E. Okay, that's the difference here. So NH3 and H2O, these are named aqua, amine and aqua. But otherwise, all the neutral and cationic ligands will have same name. Okay, I will be explaining. Carbonyl we will use for CO. You know CO is carbonyl group, CO. And nitrosyl for NO. So you will not say nitric oxide. NO is nitric oxide. You will use nitrosyl. These are placed within enclosed marks, that is parentheses. When I do the examples, it will be more clear. For now, you need to remember, if the ligand is anionic, it will end with O. H2O, aqua. NH3, amine. CO, carbonyl. NO, nitrosyl. So remember, most of the students get confused when they write NO2 and NO. NO is nitrosyl. So whenever you say nitrosyl, it is NO. Prefix mono, di, and tri, etc. if you have more than one ligand. Now important point. Instead of using di, tri, etc., if the names of the ligands include a numerical prefix, Then the terms bis, tris, tetrakis, or 4 are used, the ligands to which they refer being placed in parentheses. For example, understand it. If I say here, this one, this will be named as dichlorobis triphenol, sorry, it is PS3. Okay, phenyl is there. So triphenyl phosphine. Now, why I have used bis? Because I already have a tri here. Okay. So this is anyway will be written in bracket in the case of formula also, in case of name also. And because I have to write here by, I will not write here by. Why should I write by here? Because I have two such compounds, two such molecules attached. But for this, I will not use by. Why I am not using by? Because it already has tri written here. So 2 by tri will not be in succession. Okay. And the same thing applies if here it is, for example, 2 chloro like this also. So if there is 2 here, then also you will not write by or tri outside the bracket. You will use bis or tris or whatever, tris or tetrakis, whichever is applicable. So if you already have numbering here, you will not use by, tri, etc. You will use bis, tris, tetrakis. Is that clear?
You need to say that when a ligand has again some substance, then we use this tetrakis.
Yes. In simple way, you cannot have 2 by or 2 by, tri, etc. in succession. Same types will not be in succession. So if you see same types in succession, the first one will be bis, tris, tetrakis. The second one will be normal. So within the parenthesis, it will be normal. Whether you write 2 chloro, something like this, or you write by, tri, etc. Within the bracket, it will be normal. So within the bracket, it's normal. Within the bracket. But outside, you will not write same. You will write bis, tris, tetrakis. Simple. Oxidation state of the metal in cation, anion, or neutral coordination entity is indicated by Roman numerals. So, for example, if I write the name, I will write here cobalt, then I will write its oxidation state in the name as Roman numeral. Okay. So, you have to show the oxidation state of central metal atom always. Okay. In few cases, it is not written if it is very much evident and that metal atom has only one oxidation state possible. Okay, but normally that is not the case, so you should write. If the complex ion is a cation, the metal is named same as the element. For example, CO in complex cation is called cobalt, and this is important point. So just pay attention. If you are sleeping, just come out of your sleep. If the complex ion is an anion, means it is this, like this. It is anion. Then the name of the metal ends with 8. And remember, there are exceptions. Few exceptions are there I will be talking about. So I will not say cobalt now. I will write cobaltate. Is that clear what I am saying? Okay. So if you are writing here, it is something CO and then something here, but here there is negative sign. Then when I write the IUPAC name, the cobalt, it is cobalt. So cobalt will end with 8. So you will write cobaltate in this case. So in this case, it will be cobaltate. And in this case, if it is CO and some parts, it is positive, then it will be cobalt. And obviously the oxidation state. Clear? So for example, in this one, it is because it is anion, this will be named as cobaltate. Now the exception. For some metals, the Latin names are used in complex anions. So remember, it is anion, complex anion. But it is not written iron then, it is written as ferrate. Okay. If it is cation, it will be written as iron. So understand the difference. If I am saying this Fe is in cationic complex cation, then you will write it iron 2, iron 3, depending on the oxidation state. But if it is negative, then you will write it ferrate. Otherwise, iron 1, iron 2, if positive sign. Clear? This clock is passed by 10 minutes, I think, or 15 minutes. So don't just go by this clock, okay? Then the neutral complex molecule is named similar to that of the complex cation. Okay, similar to complex cation. So if it is neutral complex, so suppose it is just like this complex, or cation, naming convention will be same. Means you will not write here ironate or like that. Okay, obviously that is applicable only for negative. So here you will be writing, if it is neutral, you will write cobalt, not cobaltate. So same rule of positive will appear. Now the question, write the name of this, and now you will apply the rules. If you write the name, the ligands are written first in alphabetical order. Okay. And then I said that what is named first, whether cation or anion part. Always cationic part will be named first. So whether here coordination entity is cation or anion. Coordination entity is cation because it will have 3 plus charge. This has minus 3 charge. So you will first name the coordination sphere, coordination entity. And in coordination entity, you have these ligands. So write your answers. Just first I want to see whether you can write it yourself or not. Write your answer in the chat box. I am waiting for the answers. Okay, you will just write. Remember, one important point which was not written anywhere, because that's why that's why the problem is. If you have primary valence as written afterwards, you will just write it chloride. You will not write tri, bi, etc. There is a reason. The reason is you have already covered this in the oxidation state of this chromium. It means it is very much evident that there will be 3 negatives pertaining to that one. So you don't need to write 3 chlorides or trichloride. For this one, you will end it with chloride only. But you will first name the ligands, then you will name the metal, then you will name this one, anionic part. Basically, why you have put this one in bracket and not this one? And if not this one, why this one? One point, only one point is wrong, that you have to mention the oxidation state of cobalt. Otherwise, it's fine. Correct. Huh? Now, there is, because these are in parentheses, okay, you should be using. But even if you don't, that's right. Okay? That's right. RM1. Yes, just write the oxidation state of chromium. Somewhere there will be double M in amine. Okay, so it is not amine, it is amine. So write double M. Kartikeya also write double M in amine. Not just single. NS3 is a double MIN. Kartikeya, you have 3 water molecules, 3 water molecules. You have written oxidation state का लगता है. वो गलत ही है, बाकी सही है. Yes, correct. Correct, good. How many water molecules are there? So, right. So those who have given correct answer, I have already told them. Okay. So these are the rules just written. I am just going to the answer. You have 3 amine and AM comes first and then AQ, but you have 3 aqua, so you will write triaqua. Then chromium, its oxidation state 3, and here you just need to write chloride. I said you don't need to write how many, because that is already considered in coordination entity. How many chlorides will be there? I'm just going back. And those who gave me answer, out of those who tried, I think almost everyone gave me very close answer and or correct answer. So understand, this is positive part, so you will name it first. Within that, you will name ligands first in alphabetical order. After that, you will write metal with its oxidation state, and in the end, you will write anionic part. Okay, chloride. Now I am giving you another question which will further clarify everything. Now again, remember, this is again 6 plus. Okay. So again, it is cationic part. Cationic part is written first. This is what? En. Right? This is En, ethane 1,2-diamine. And this is cobalt. So you will first write ethane 1,2-diamine, then you will write cobalt with its oxidation state. Then at the end you will write sulfate. Simple. So tell me the answer. Avoid in your IUPAC naming. Avoid writing En, but you can. Okay. En is written in the formula normally. En is written normally in formula. So for example, here I could have written it as En whole thrice SO4 whole thrice. Or in the structure also. Okay, 3D structure. Now let me see who has given me correct answer. Tanishi, very, very good. I have not seen the entire answer because I had to close it. Otherwise, these people will see your answer. So that's why I closed it very quickly. But the initial part you have written very, very good. Okay. That's what I was looking for actually, that who will give me that answer correct. No, something is wrong there. Okay. I will see the chat answers in few seconds, because first I have to see answers here. Otherwise, these people will correct answers. No, there is slight mistake. No, still there is slight mistake. Yeah. No, slight mistake. Okay, so here no one has given me correct answer. No one has given me correct answer here. No. Pratham and Kavish, you are close, but you are making a silly mistake. Okay, I'm going to explain it. But first, let me see the answers on the website. Oh, sorry. I was actually thinking back of my mind that these people might have given me answers from the website. So that's why. Yes, okay, Kartike. First, let me see who gave me the answer correct. So, Tanishi, let me see whether the whole answer is correct or not. So, you use tris, which is absolutely fine because you have 3 ENs, not 2. You were close, but you had written bis.
The answer was.
Bis is for balancing the charge. For balancing the charge only. So, this is actually here 2 minus here 3 plus this 3 will go here and this 2 will go here. That's what we are talking about. So 2 and 3, these are the charges. These are not telling how many ligands are there. Ligands are 3. Okay. So, huh? En. It has ethane 1,2-diamine. 1,2 numbering is there. Numbering is there. Right. So Tanishi, tris, ethane 1,2-diamine, cobalt 3, yes, sulfate. Good. Good. That is the answer. Okay. So cationic part will be named first. Within cationic part, you will name the ligands first. And for ligands, you could have said tri. But remember another rule. Whenever you have to write something in brackets, ligand, ethane 1,2-diamine. So you can get a clue from there also that it will be not ditri, it will be base, tris, etc. Okay, but that rule is not 100% correct because you write H2O, NH3 also in brackets. So the 100% correct rule is there should be some numbering. So ethane 1,2-diamine, there is numbering. So you will say it will be tris, and then you will write ethane 1,2-diamine, ethane 1,2-diamine. Remember here I am writing single M because it is amine. It is not NH3. Then I will write metal, cobalt, with its oxidation state. Oxidation state, how did I get it? X, and En is neutral, 0 equals to 3. So X is 3. Then sulfate, and I have told you that whatever is outside, you will not write how many these are. This is the answer.